69% of VCE chemistry students scored 0 on a single electrolysis question on the last exam. Why? Because they forgot the golden rule of industrial chemistry. There is no such thing as a free lunch. Every process change comes with a hidden scientific cost or a data book trap. Hello everyone, and welcome back. I'm Dr. Liu. Today, we are breaking down the trickiest multi-mark exam questions. I'll show you exactly how to use variable control logic and the goal mechanism framework to lock in your constants and write precise, full-mark responses. Let's get started. Steph is an engineer working in the electroplating industry. Electroplating is a process that uses electrolysis to coat objects with a thin layer of metal to protect the object or improve its appearance. Traditionally, objects are electroplated with chromium, Cr, using the setup shown below. The electrolyte used is chromium, 3, sulfate, Cr2SO4, 3Aq, with a small amount of sulfuric acid, H2SO4, Aq. To earn the full 2 marks, the response must be structured as follows. Identify the oxidation numbers, Mark 1. The oxidation number, ON, of chromium in Cr3+ is +3, and the ON of chromium in its elemental form CIS is 0. Justify the process, Mark 2. Because the oxidation number decreases from +3 to 0, the reaction is defined as a reduction process. Critical don't lose marks checklist. Based on the official assessor comments, ensure students avoid these specific errors. Sign order matters. Always write the sign before the number for oxidation states, e.g., +3, not 3+. Using 3+ is the notation for ionic charge, and is a frequent reason students lose the first mark. Stay on prompt. If the question asks you to explain using oxidation numbers, don't just say it gains electrons. While true, you must explicitly mention the decrease in numerical value to satisfy the marking criteria. Precise terminology. Use the phrase decrease in oxidation number rather than decrease in charge. Highlighting the same ion as the conceptual anchor is a brilliant way to help students visualize the loop of the system. In VCE chemistry, precision is everything. Other essential keywords are both the anode and cathode, which signal that students must explain the reactions occurring at each electrode to show how they work in tandem, rather than just describing one half of the process. By combining these 3 specific anchors, the same ion, the anode, and the cathode, you ensure students capture the full spatial and chemical loop required for a commercial system. Here is the reorganized response, structured specifically around the goal mechanism framework. Question 2b, Model Response. Goal, Mark 1. For effective commercial electroplating, the concentration of Cr3+ ions in the electrolyte must be kept constant. This maintains a uniform deposition rate and ensures the consistent quality of the metal coating. Mechanism, Mark 2. This balance is achieved by involving the same ion, Cr3+, in both the anode and cathode reactions. The Cr3+ ions are produced at the anode through oxidation, at the same rate that they are consumed at the cathode through reduction. If a student omits the mention of both electrodes, they fail to describe the loop, and typically miss out on the second mark, even if their chemistry is otherwise sound. Highlighting the phrases small amounts, and carefully managed, is the best way to help students understand the delicate balance of an electrolytic cell. These terms act as the conceptual anchor for the entire problem, signaling that the user must prevent a competing reaction from ruining the industrial process. By focusing on these anchors, you ensure students recognize that in VCE chemistry, a change in concentration can shift the standard expectations of the electrochemical series. Here is the reorganized response, structured around your goal mechanism framework. Question 2C, Model Response. Goal, Mark 1. The amount of H2SO4 must be carefully managed because H+ is a stronger oxidant than Cr3+, as its half equation is higher on the electrochemical series. The goal is to keep H+ in small amounts so that it does not outcompete Cr3+ for reduction at the cathode. Mechanism, Mark 2 and 3. If the acid concentration is too high, a competing reduction occurs where H+ ions gain electrons to produce hydrogen gas instead of chromium metal. This results in plating failure. The object will not be electroplated because the electrons are being used to produce gas rather than deposit CIs. Safety risk. The production of H2 gas is flammable and creates a hazardous working environment. The 60% zero mark rate indicates that this question is a true separator in the VCE exam. To help your students join the 10% who achieved full marks, we can break down the pitfalls using the specific anchors that cause the most damage. Highlighting small amounts and carefully managed as the conceptual anchors is essential to avoiding these traps. These phrases signal that the industrial success of the cell depends entirely on preventing a competing reaction from becoming the dominant process. By focusing on these anchors, you ensure students recognize that precision in terminology and a clear understanding of the electrochemical series are the only ways to survive this marks killer. Here are the reorganized pitfalls. Warning sign # the marks killer pitfalls, why 60% got 0 marks. 1. The terminology trap. Cr is the oxidant. The error. Many students wrote that Cr is a stronger oxidant than H+. The reality. Cis is a metal, a reductant. It is the Cr3+ ion that is the oxidant. Failing to distinguish between the metal and the ion results in an immediate loss of the first mark. Correction. Always specify the ion, Cr3+, when comparing oxidizing strength on the SEP table. 2. The identity crisis. H2SO4 is not H2. The error. Responses implied that adding H2SO4 directly creates H2 gas like a simple chemical mix. The reality. The gas is a product of electrolysis. H+ ions from the acid are reduced at the cathode to form H2G. Correction. Explicitly state that H+ undergoes a competing reduction reaction. 3. Ignoring the small amounts anchor. The error. Students fail to explain why the amount matters, simply stating it's just an electrolyte. The reality. Because H+ is a stronger oxidant than Cr3+, it would normally be reduced first. We use small amounts to lower its concentration, shifting its reduction potential to make the reduction of Cr3+ more favorable. Correction. Use the goal mechanism logic. The goal is to manage the concentration, so H+ doesn't outcompete the Cr3+. Electric light bulb summary for students, the full marks checklist. To avoid the 60% fail rate, your answer must include relative strength. State H+ is a stronger oxidant than Cr3+. The competing reaction. Identify that H2G will be produced at the cathode. The result. Explain that this ruins the plating or creates a safety hazard. Goal. To calculate the constant current, I in amperes, required to deposit the given mass of metal over the specified time period. Mechanism. This is achieved by linking the mass of the metal to the total charge, Q, pass through the cell using the stoichiometry of the reduction reaction. Identify the cathode half reaction. Refer to the half reaction at the cathode first to determine the molar ratio shows 3 moles of electrons are required for 1 mole of metal. Calculate moles of metal, N. Convert the given mass, m, into moles. Calculate moles of electrons. Use the molar ratio from the half equation to find the total moles of electrons dissipated. Determine total charge, Q. Calculate the total electronic charge by multiplying the moles of electrons by the Faraday constant, Q equals N, E times F. Solve for current, I. Since Q is equal to current multiplying time, rearrange the formula to current equal to Q divided by time. Substitute the charge and the time, ensuring time is converted to seconds, to find the current in amperes. The calculation killer, pitfalls. The ratio anchor. The most common error is using an incorrect molar ratio. Students must identify exactly how many electrons are required for the specific ion being reduced. Time conversion. A frequent mark killer is plugging hours or minutes directly into the formula. The relationship Q equals I times T strictly requires time in seconds. Significant figures. Final answers must be rounded according to the precision of the provided data to maintain scientific accuracy. Model response, goal mechanism. Goal, Mark 1. To plate the same mass, 7.80 g, a smaller amount, moles, of rhodium is required compared to chromium. This is because rhodium has a much larger molar mass, 102.9 mu, than chromium, 52.0 mu. Since both Rh3+ and Cr3+ ions require 3 electrons per atom, rhodium requires fewer total moles of electrons to reach the target mass. Mechanism, Mark 2. Because the total charge, Q, required is lower and the time, T, remains constant, a lower current, I, is needed. This is because current is directly proportional to the moles of electrons transferred over a set period. This pie chart from the official VCAA examiner's report reveals a harsh reality. 69% of students received 0 marks for this comparison question. Only a small elite, 23% of the cohort, managed to secure the full 2 marks. Why was the failure rate so high? The examiners noted that the majority of students fell into intellectual traps by failing to hold variables constant. The voltage red herring. Many students were distracted by the E0 values provided in the question stem. They tried to explain the current using electrode potentials, which determine spontaneity, not the quantity of charge required. Breaking the logic chain. Many fail to explicitly state that because both Rh3+ and Cr3+ ions carry the same charge, the only variable left to consider is the number of atoms, moles. Variable confusion. Students struggled to link the higher molar mass of rhodium to a lower required current when the mass and time are fixed. The 23% club strategy. To join the top performers, you must use the variable control logic. By pinning down mass, charge, and time, you reveal that rhodium's high molar mass is the only reason less current is needed. To get full marks on a VCE comparison question, you must demonstrate variable control. The goal is to identify which factors are held constant and which single variable drives the final result. When comparing the current required for rhodium versus chromium, we must apply a variable control approach. First, we acknowledge that the mass and the plating time are held constant. Crucially, We must also recognize that both Rh3+ and Cr3+ ions carry the same charge, meaning they require the same number of electrons per atom for reduction. The deciding factor is the molar mass. Because rhodium has a much higher molar mass than chromium, a smaller amount, moles, of rhodium is required to achieve the target mass. Consequently, a smaller quantity of electrons, and thus a lower total charge, needs to be transferred. Since current is the rate of flow of charge, a lower current is required to plate the rhodium within the given time frame. Avoid the voltage trap. The E0 values, plus 0.76 V versus 0.74 V, are irrelevant here. They tell you about the spontaneity of the reaction, not the quantity of charge required. Don't forget the charge. If you don't mention that both ions are +3, your logic for comparing molar masses is incomplete. Watch the proportions. Remember the inverse relationship. As molar mass increases, the required current decreases for a fixed mass and time. Variable control logic, rhodium versus chromium. To successfully explain why less current is required to plate the same mass of rhodium compared to chromium, students must apply variable control logic. Goal: the why. Because rhodium has a significantly larger molar mass, 102.9 mMu, than chromium, 52.0 mMu, a smaller amount, moles, of rhodium is needed to reach the target mass. Since both Rh3+ and Cr3+ ions require 3 electrons per atom, rhodium requires fewer total moles of electrons for the same mass. Mechanism: the how. As the total charge, Q, required is lower and the time, T, remains constant, a lower current, I, is necessary, as current is directly proportional to the moles of electrons transferred over a set period. Critical examination pitfalls: the 69% failure analysis. Data shows that 69% of students failed this question by falling into specific intellectual traps. The voltage red herring. Many students incorrectly tried to use E values to explain current. Electrode potentials determine spontaneity, not the quantity of charge required. Emitting cation charge. Logic is incomplete if it does not explicitly state that both ions carry the same +3 charge. Without this pinned variable, the molar mass comparison is invalid. The inverse relationship. Students must recognize that as molar mass increases, the required current decreases for a fixed mass and time. If you need my help, please add me on WeChat or WhatsApp and send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.